Okay, my streaming software says I am live. So here, this on the stream is going to be WASI Preview1 documentation writing. We're going to go through the Preview1 API and also the ABI and talk about what's going to just more documentation for the functions in Preview1, and also documentation for things like how does the witx, the ABI part, how does the witx map onto the header files. So I'm going to pull up HackMD. It'll take me a few minutes to get set up here. I'm not totally set up yet. And start sharing my screen. So I get this all set up. So Preview1 is based on Cloud ABI, and it has a number of modifications and simplifications to better meet the needs of WASM. But it's also still very POSIX oriented. It's very much a simple POSIX-like API. witx is also a C ABI. There are some things in the witx syntax that ended up sort of anticipating features that would end up being in the component model. You see syntax for things like result types and string and array types. But at the time when we developed witx, we didn't really have a real component model. We didn't really have real string or array types. We kind of made result type work. But overall, the system is not super sophisticated. So I'll dive into that a little bit, and I'll figure out where I am here. Okay, new note. Okay, I'm going to share my screen with the HackMD window, and I'm going to do some editing live here. So let's get that set up. Start screen sharing. It's going to be this window. All right, so now I am sharing my screen. Hello, I got one person in the chat. Yeah, it's good to see everyone. I don't expect this to be a super popular stream. We're not going to get tons of people here, but if anyone wants to show up and be part of it, I will monitor the chat and answer questions that come up. So still taking a few minutes to get everything set up here. I've got my HackMD window that I'm getting set up, and I'm going to do a pull from GitHub. So the Preview1 documentation now lives in the WASI repository, and it lives in a directory called Legacy because we're working on Preview2 is the big thing forward. That's going to be a major milestone for WASI that it's going to make a lot of things possible when we move to Preview2. But right now we're talking about Preview1 and documenting Preview1. So we're going to go to the witx file. Let's start with the type names.witx file. So the witx files for Preview1 were split into two files. There's the types files and there's the Preview1 documentation file. So let's dive into types.witx first. It's going to be this file, and I'm going to go and pull it in here. I might need to be able to use my own repo here. So let me just see if I have. Yes, okay. I need to do this. So HackMD is the editor I'm using to do this. HackMD wants to pull it from my own GitHub account. So I have a fork of the WASI Pro. I'll just be updating. Okay, I got a few things to clear out here. Okay, so now my github.com/sunfishcode/WASI repository is now up to date. At least the main branch is up to date. Or it should be. What did I do here? Oh, that was the wrong WASI repository. Okay, I made a mistake here. I'm making mistakes on the fly here. Let's start something new here. So we're taking the WebAssembly WASI repository. I'm going to sync it with my own WASI repository. And the master branch is the default, but we're using main, and now main is up to date. Okay, so now we have sunfishcode/WASI tree main is up to date. Now I can go back to hackmd and do this. Do that. Okay, I need to authorize more repositories. All right, so I apologize for a little bit of a run around getting things set up here. All right, my authentication code did not work. Okay, so I'm having issues getting this set up here. Get my hackmd to GitHub sync working. So I'm going to try to stop doing something fancy here. Instead of trying to pull from GitHub, I am going to do something much lower tech just to get something working here. And I will resolve this later. I'm going to copy and paste. Okay, so make this window a little bigger. So this is type names.witx. This is the main file that defines the types, struct types, also integer type defs, and enums in the Erdo code. Let's just make this my zoom out here. Hopefully this is still readable on the screen here. So type names used by local WASI interfaces. So I'm going to edit this. This is just a copy and paste thing, but I'll form this into a regular PR after this live stream is over. So here we go. We got some here from C ABI. So witx file. And already we have a broken link because that's no longer the right link. But do we have docs.md? That was a generated file. Preview1. All right, so the first thing I'll put in here is the description of what witx is. The C ABI types and functions. It's based on the assumption memory is exported. These are core WASM types. All right. All right, so this is going to be our top level comment. And dive into it. So type name size, this is the size T type. So the idea for this type originally was that WASM has a 32-bit memory. The memory indexes are 32-bit. And so WASM 64 is coming. We've known it's been coming for essentially since WASM was first released. We kind of anticipated that WASM would have a 64-bit version at some point. And so we add this type def to allow functions that could continue to refer to any size of something in memory to have a type, much like the C size T type. And so this is what this is. It's a type def for U32. It looks like at this time we won't be developing a 64-bit version of the Preview1 APIs. They could be done, and they could be done by changing this type def, but that's a lot of work. And at this point, there's no one stepping up to volunteer for that work. And so it makes sense then to focus the work on people where people are volunteering to work, which is on advancing Preview2. So this essentially is this type def, just U32. It'll probably always just be U32 then at this point. In your memory. All right, so let's keep walking through this file. File size. Historically, systems have had different types for their file size offsets. But in even reasonably modern times, all systems have moved to 64-bit offsets because files can be larger than 4 gigabytes. And so even 32-bit platforms are moving to have 64-bit file sizes. So for WASI, we decided that we're just going to make all file offsets, file sizes be 64-bit, so we can always handle files greater than 4 gigabytes. So this corresponds to T in POSIX. All right, timestamp in nanoseconds. And this is not just nanoseconds, it's also nanoseconds since the epoch. We're going to say Unix time, timestamp in nanoseconds. So Unix time is the name of the time system that WASI uses in Preview1. It's also in Preview2. And it's based on the system of measuring the number of seconds, or in this case, nanoseconds, since essentially January 1st, 1970. A U64 of time can represent any time up to something like 500 years from now, give or take, which this observation came from Cloud ABI. Cloud ABI also has just a U64 of nanoseconds since the epoch for its times. And arguably, 500 years is a long time, longer than computers themselves in any kind of recognizable form have been around. And so it's not really possible to predict how long the APIs we're designing here could last, if they could possibly last more than 500 years. That's not really, there's no basis by which anyone could predict that. So a U64 of nanoseconds is certainly good enough, and hopefully Preview1 won't be along for 500 years. In Preview2, we've actually moved to a pair of numbers. We have a number of seconds since the epoch, which gives us a 64-bit number of seconds since the epoch is many, many more seconds than we could possibly imagine, plus nanoseconds. So we kind of break past the 500-year barrier in case that's relevant. Okay. So Preview1 has this idea of enums, which are basically C-like enums. They have concept of a tag value. This would eventually anticipate the development of variant types in the component model. But here it's still sort of very basic, a C-like union that we'll eventually have for the clocks. Unions and enums, essentially C layout types. So we got clock ID. It's a witx thing. These are already pretty well documented, I think. I'm going to take the opportunity to remove the process and thread CPU time things. These were removed from recent versions of Preview1, and they're not supported in most engines at this point. So the reason why we took out process and thread CPU time, we took those out of the API because it's very common to have WASI instances that are not per process. We have many WASI instances in a single process. And that's actually a big advantage of many WASI use cases, is that we don't have to take on the overhead of a whole OS process for each WASI instance. But that means that we can't simply use the host OS clocks for things like the process or the time, because you might be sharing a process with other instances, which means some of the time might not be your time, might be time for spent in another WASI instance. And so it wasn't, there are theoretically ways to implement this for WASI. We could have engines essentially do their own timing on entry and exit to a WASI module. But these clocks aren't used all that often, and it seemed to blur at the time to just remove them. So I'm going to remove them here now as well, just to make the documentation and the API simpler. Those types are also not present in Preview2 either. So it's kind of the path forward is to not have those clocks. So we just have two clocks. There's the real-time clock. Time. I mentioned that it's Unix time. The clock version real time is Unix time, which is the time value 0 corresponds with January 1st, 1970, the Unix epoch. And there's also monotonic, which is just real-time clock, which has a commonality. Then we get error no codes. I'm going to skip over these right now because these are basically just POSIX error no codes. I don't think there's anything particularly interesting to do. One thing I can note over here is that some of these error no codes are renamed from POSIX, so we don't have the prefix E, and I guess we didn't fix the spelling for access in the end. But they're pretty straightforward, and they closely correspond to POSIX error no codes. The one interesting one here is this not capable one at the end. This is something we get from Cloud ABI. Cloud ABI, which also gets it from Capsicum, has an additional error no code, which is not a POSIX error no code or any other Unix. It's E not capable, which they use whenever the guest application requests an operation that doesn't have capabilities for. And what this typically means in Cloud ABI is that Cloud ABI has a system of what's called writes, where every file descriptor has a bit field associated with it that has a set of things you can do with it. And we'll get into the writes. Actually, that's the next type we're going to type into that a little bit. And so the writes field, we have all these different bits for, okay, given a file descriptor, can you do a data seek with it? Can you do a read with it? Can you do a seek with it? Can you do a sync with it? Can you do a tell, which is like, tell me the current offset? Can you do a write, advise, allocate? So there's essentially a bit flag, a bit field for everything you can do with a file descriptor that can be set or unset. And that can be used to make somewhat fine-grained control over what someone can do with a file descriptor. And so if you ask to read on a file descriptor that doesn't have the read bit set, then you'll get this E not capable error message. And if I don't know this. All right, just in retrospect, not capable ended up being kind of awkward for us in WASI because it's not in POSIX. So portable applications aren't aware of it. It just comes as extra error code. And in fact, there are many places in libc where we end up, and Cloud ABI's libc does this too, where it takes the not capable error from the system call and translates that back into a POSIX-like error code. So if you try to read a file descriptor and you get not capable, because it's missing the read byte, it'll translate back into, I think that's bad F, is what POSIX says for the error code for reading from a file descriptor that's not readable. So WASI libc itself is going to be like trying to cover up the not capable in a bunch of cases, like similar like E not sock or sort of things on operations on sockets. And so it's like if WASI libc is going to end up hiding this for applications anyway, and this isn't in POSIX, it doesn't seem like this is a great thing to have in WASI itself. And so in Preview 2, we've taken out not capable, but it's still present in Preview 1, so it's gonna leave it here. All right, so I just talked briefly about the write system. So this write system, as I mentioned before, it's that there's a bit for everything you can do with a file descriptor. But one of the problems that it has is that this system has a very few things that it's actually good for. You can get somewhat fine-grained control, but you can't have you can define things like can you append to a file or not, but you can't define things like how much can you append, or can you append within certain sizes, or can you append and do a non-atomic append. Your ability to limit what someone can do with a file descriptor is limited by the bits that are available. So it's somewhat limited in that respect. And on the other hand, it's also somewhat more expressive than most people ever need. In practice, looking at what people did with WASI in practice, it's always been like the one thing that I know of that actually writes are useful for is making directories read-only. And so if that's the only thing we're doing is saying, like, well, we'll give you a handle that says you can do things with directories or only read only the directory, then we don't need a whole write system to do that. We just need a concept of read only directory. So in Preview 2, the write system has been entirely removed, and we just have a facility for opening a directory in read only mode. So we can have the whole directory be read only, or have a read only view for it for a guest to work with. So this write system is also pretty notorious for being really confusing because it's always been unclear who needs what writes and when, and how these writes map onto POSIX, because the write system is not something that's present in POSIX, so most people aren't familiar with using it. In fact, the direction that I and others in working on WASI time have been heading in is just to use the write system in Preview 1 as minimally as possible. We sort of need to have it for things like the read and write bits, but not to be too strict about it for other bits, because just not that useful, and it's not the direction that Preview 2 is heading in anyway. So I could maybe add something about that here. Okay. Okay, so hopefully that's some more context. And I hope that when people are implementing these APIs, if people have questions, I hope that they file issues on the WASI repo. We can additionally help clarify things. This will also be, and there's a process in place for this that's been going on about adding tests to the WASI test suite, which will also help kind of flush out some of these kind of questions of exactly what do we need to do here. But hopefully this little bit of blurb documentation will be enough for now. And I'll reformat this and submit this as a proper PR offline after this live stream. So let's keep scrolling through. I'm kind of taking some time here, but I'm going to skip through all these writes for now. And I think IOVEC, these are all pretty well commented. The interesting part is we're going to get to the interesting part later on. I think this is not the stuff we need to focus on right now. So then I wanted to get to that rights event, right stuff, and we'll talk more about some of these things in the context of signal conditions. Yeah. Okay, I got a question here. How much of this documentation carries over Preview 2? You mentioned Unix time changed. Yeah, so I actually did a live stream for Preview 2 documentation earlier, and I believe we documented things like the time type and that kind of stuff. So I'm also keeping track of things that we're doing here that should be documented for preview 2. I think we're pretty well covered here. The main things I want to cover today is like the low-level stuff we're playing the ABI. But yeah, it's a good point that preview 2 has a lot of the same APIs, and we've made some changes, and those changes I believe are pretty well documented. If you go to WASI file system, the repo here, and take a look at, or actually this would be WASI clocks for this topic with so for the curious, you can see WASI clocks in preview 2 is documented here, so we have all the stuff covered there pretty well. So right now we're working on preview 1 and like filling in the areas where we're covered very well. So I'm going to, unless I don't have any particular things in the chat that we want to cover here, I'm going to go ahead and save this types document, because I think the interesting part is going to be the next file when we get to snapshot preview1.witx. That's going to be where a lot of the bulk of the interesting stuff is. So because my GitHub stuff is not working live for some reason, I'm going to do another high-tech copy and paste. First, I'm going to save this. Create a new note. Okay, so we got our, this is WASI snapshot preview1.witx. This is the main witx file that defines all the functions here. And we got Cloud API. And so use type names.witx. This is actually part of that for historical context, the X in witx. So wit originally referred to this as expression format, which sort of just described the signature of a core WASM module. And then witx was like extensions to that to make that wit format into something more like an IDL with the ability to have types defined in separate files. And we have this kind of use construct. In practice, this use construct isn't super sophisticated, but it worked at the time. And so we have type names.witx. Pulling on the types we just edited. So now we have this module. So again, this is sort of like the S expression format, sort of defining a signature for a core WASM module and what it can do. So we describe the import. That's how the outside world is going to conceptually import the memory by the name memory from the application. And so this is how we can be able to pass pointers from the application to the host by saying, I'll pass a pointer, and the host will import this memory from the application and then index into the memory with the pointers. Okay. So we're going to walk through these functions, and we're going to document things as we go. And also, I'm going to keep another page to keep track of ABI things that we need to document. And so I'll get to those as we go. So first thing we have is, zoom out a little bit more to make this a little more readable, argsget. So command line arguments. This is the system by which the start function has that is the entry point for WASI Preview1 programs, has no arguments and no return values. And so the way we can get command line arguments in is to have these argsget functions, and it's kind of this two-step dance. Let's see. Yeah, so the size of the array should match the return by argsget. So to use this function, first call, let me just write this in. arg sizes get. So there are two sizes coming back from here. One of them is the size of the array of, the other one is a really big array of all the strings, and the pointers will point into different points in that string. All the commanded strings, all the arguments. Okay. So you call arg sizes get, and I'm going to pass in argv, which is a pointer, pointer to the string. The size of the arrays should match the sizes returned by arg sizes get. Each argument is expected to be null terminated. The first argument should be a string, and first command argument should be a string containing the name of the program. argv0, it's actually an interesting question about what argv0 should mean for a WASI program, because not all programs are invoked via a normal command line process. And so what should argv0 be when you don't have that? Preview1 does not end up having an opinion about that. It just kind of waves its hands and says there needs to be a string there, but we're not going to say what it is. So null terminated strings for all the arrays. And let's keep going here. Subsequent arguments are the arguments passed to the program by the user. Okay. So then we also have this function for arg sizes get, and this is the function that returns the sizes for okay. So quickly say some things about this. All right, so get. All right, so the really interesting thing that we want to cover in this is all these functions where Preview1 ends up doing this a lot, where we say this is similar to clockget, res, and POSIX. We don't really say what it does. Return the resolution of a clock. All right. Give it a clock ID and an error. Okay, so here we got a result type. I'm going to copy and paste this into my other tab here. So result types are essentially variants where there's one arm for the success case, that's the expected case. So clock ID will return a timestamp on success and an error no failure on error. And so it's essentially like a variant, which is like a discriminating union with a discriminant that tells you is it the success or failure case, and then depending on which case it is, there are different fields for the success value, the timestamp in this case, and the failure value. So clock time get. All right, I think this is pretty well covered already. It does have the similar to clock time get time in POSIX, but we have pretty good documentation for what the parameters say, maximum lag, for return time. In fact, I should look up clock time get. What does WASI libc do when it calls this function? So this maximum time is something that Cloud ABI invented, and it's kind of novel and not used very often because it's not in POSIX. And so, yeah, I think that's going to be the answer. Is like if you don't know what to do there, you could pass 0 or 1. The idea is, let's see if I can put this in words here. Okay, so it's an interesting idea. There's a number of interfaces in libc that historically POSIX defined or Unix defined to take microseconds or even milliseconds in some cases. And so if you're one of those functions and you're going to call the clock time get function, and you don't need nanosecond precision, because you only need microseconds or milliseconds, then you can tell it that. And then in theory, there could be implications where you could read from a coarse-grained clock, which might be faster than reading from the most precise clock. In practice, I don't actually know of any implications that ended up actually making use of this. And I don't know that Linux has a way to do it. In fact, Linux has a very fast way to give you essentially the most precise time with the user space VDSO mechanism. And so in practice, this ended up being very useful, and it's been removed from Preview 2. Removed from Preview 2, but now at least I've explained what this means in Preview 1 and give people a clue of, like, if you don't know what this is, just pass 0 and don't worry about it. And get time values on the clock. Keep going. FDadvice. Provide a quick note about what advise means. All right, so yeah, so FDadvice is all about giving people an implication hint here. Okay, so that's FDadvice. Let's keep going. FDallocate. This ended up being a really weird system call, which is also removed from Preview 2. It's tricky to even describe what this function does because it gets into the very low level semantics of POSIX files, where you can have you can allocate space in a file beyond the actual data extent of the file. And then the theory is, if you do that, then you can guarantee that subsequent attempts to increase the file size will succeed, because you know you've already allocated the space for it. This concept doesn't really apply very well outside of that very specific POSIX context. It doesn't really apply to Windows very well, and so we've taken it out in the interest of portability. It's also not very widely used, in part because it is kind of so subtle, and there's not really many uses for it. So this is an area where potentially there might be a place for, in the future, a WASI API that could be more specifically targeted toward POSIX. I think WASI in its current form, there's a pretty wide desire to have a WASI API that works across both POSIX and Windows, and that means we need to make certain compromises. I think there's potentially in the future a space for a WASI API that could focus more specifically on POSIX and just accept the portability trade-offs. It could work with this API and extend it and add things like fallocate. But right now, I think it does make sense to focus on this more portable set and really maximize the portability gains, because most things are pretty well portable. There certainly are a lot of differences between Windows and Unix, but you can do a lot with the common subset. There's another function which is similar to this, which is called truncate, which will actually change the actual size of the file. So you can truncate can make a file smaller or larger, and when it makes it larger, it fills it in with zeros. And that's an operation that we can do in a portable way, which makes a lot more sense to have in WASI. All right, so we have the file descriptor, the file to operate on. And we got offset allocation. Okay, so this is the file descriptor. Next, that technically wants most once for every file descriptor. Now, you don't technically have to close things. You can exit the process with open file descriptors, and the system will clean those up for you. Yeah, so once you have a closed file descriptor, it's important to not ever use it again, in particular because file descriptors are just numbers, and the numbers get reused. So if you continue to use a number after you've closed it, you have the risk of using a file descriptor that's been aliased to something else. And the error case is interesting for close. So in POSIX, close returns an int, which can be 0 on success or -1 on failure. And it turns out that close failing is actually a really complicated thing to deal with. Because if you're trying to close something and it fails, what should the application do in response to that close failing? Because you can't close it again because you've already closed it, or you've already risked potentially closing it twice. So there's kind of this question of like, if close fails with an interrupt failure, you don't have very good options. And also, if you are any kind of class, any kind of language with a destructor system like C++ or Rust or other languages, it's really awkward to have the close call in the destructor fail because the destructor, we want to throw an exception or return an error code from the destructor. And so in practice, even in C, it turns out that it's awkward to handle errors from close. And so in practice, Linux basically guarantees that close will never fail, and many other OSs do as well. It's not totally true if you have a network file system like NFS, because NFS plays certain games under the covers to defer certain error messages in order to go faster. But I think the observation for WASI from the point of view of a portable program that wants to have predictable behaviors, you could basically assume that close will never fail. And then on NFS, if there is a problem, we can assume that the problem will get caught by the system administrator, which should be monitoring for things like running out of disk space or IO errors or corruption, that kind of stuff. Those should not be the possibility of an application to monitor for with NFS. There's a lot more that can be said about that topic, but in general, we can basically assume that close should not ever fail. And that's a trade-off to be sure. We can look at network file systems, but it also helps us make sure that we have a predictable system that we can write applications to, and applications know what their expectations are. They know what happens if they call close. They don't have to worry about, am I expected to handle some kind of error code here? All right, let's check on my chats. All right, yes. So walking through, and we're going to have FD data sync. not defined in WASI. Maybe I'll say it if I okay. Get the attributes of a file descriptor. So FDadvice. FDstats. So go back to here and go to our type names. So our FDstats, we get, so this is what FDstat is going to return this kind of record. It's going to have file type in it, file descriptor flags, writes that are part of this file descriptor, maximum set of writes that we installed to new file descriptors that are created through the file descriptor to path open. All right, hang on 1 second. I'm going to go here. I'll be right back. All right, I'm back. So over here, we're talking about FDstat. So this says where the writes can be queried. You can query what the writes are. All right, this is pretty straightforward. I don't know other ideas off the top of my head what to add here. Just okay, the desync, rsync, and sync flags may not be set. Pinned to non-block. Okay, let's do fdstat set writes. Adjust the writes of file descriptor. Clean this up a little bit. So that the return's not capable if you have to change any writes. Okay. Attributes on file. FD file stat get. So this is similar to fstat in POSIX. The file stat is the similar to the stat structure in POSIX. So file stats, we got the usual stuff here. Okay, FD file set size is similar to ftruncate in POSIX. We talked about earlier about ftruncate being a way to okay, set times. Okay, go to FD pread. This is where we are very similar to pread in pread in POSIX, but in this case, we actually have the IOVAX who are pread function in the Excel Unixes, which is not a POSIX thing, but it's pretty common. So I think these are pretty well covered. We'll talk more about the. In fact, we'll go to here and talk about this thing, the IOVAC array. That'll be a particular thing we want to talk about a little bit later. And keep going here with FD prestat get. FD reader. So reader is a particular thing that we get this from Cloud ABI, and it turns out to be really complicated. Conceptually, what it's doing here is you have a handle to a directory, and it returns a sequence of directory entries, in the directory. It's conceptually very simple, but in practice, what happens is there's this buffer. You have to provide the buffer, and it has to fill in the buffer with entries, and the entries are variable length because they have a string in them. And then there's kind of this question of what to do at the end of the buffer when the next entry doesn't totally fit. I think where we ended up is that this function should not try to handle partial or write out partial entries because those aren't very useful. But let's see if we can tidy up a little bit here and see what we can say. So little contents output directory entries, just a direct object. So in preview 2, this is also something that is significantly simpler. In preview 2, we literally just have you call read entries, and you get an iterator that will iterate over the entries. But here we have reader. It is what it is. Instead of saying that it fills the up buffer as much as possible, truncating the last entry, that behavior is not actually useful. I don't believe implementers are doing that. Oh man, so I forgot about this. The number of bytes stored in the read buffer is less than the size of the read buffer. That's how you know the end of the directory has been reached. Okay, that's really, yeah. This API, I think, really suffers a lot from the limitations of witx and C ABIs because we're trying to pack information about, like, did you hit the end of the file? Is sort of the special case of the number of bytes we returned, and that essentially requires us to have this behavior of you have to write in a partial entry so users don't think that you stopped because you're at the end of the directory. So I'm going to erase this, and I need to come back and research this because I don't actually remember where we ended up on this in terms of implementations, because I don't think we have implementations all writing the end of the writing truncated entries, but that's what the documentation says, and it might have to be that way. So I have to come back to this. Time to replace a file descriptor. All right. All right, that was kind of a confusing thing to say originally. Okay, that comment is actually just inaccurate, and we're going to delete it. So FDV number, just a historical note here with FDV number. Dupe in POSIX is a little bit weird, and we wanted to make sure that we understood what that meant for WASI. early on. We kind of knew that we didn't really want to commit to having the full dupe thing before we really understood it. So we added this FD number as sort of a very limited form of dupe, where it forces the original file descriptor to be closed. That way, we don't have to worry about the awkward case of having two file descriptors for the same file. Because it is actually pretty weird that when you have two file descriptors for the same file, they share a current position. So if you do a read from one file descriptor and then a read from another, the second one will continue reading where the first one left off. So these two file descriptors kind of are connected with their current position. And that was behavior. We didn't necessarily know if we wanted to preserve that in WASI. Now with Preview 2, I think it's pretty clear that we've moved that behavior into the WASI platform no longer has a concept of file descriptors having a built-in offsets. User space can implement streaming through a file or maintain its own offsets if it needs to. And so this doesn't come up anymore. But and so I think in Preview 2, we'll have a proper dupe. But here, historically, we made the choice to not have it, since that's where we are. Okay. FD seek. All right. Synchronize data and metadata to the end of the file, similar to fsync and POSIX. Okay. FDTell. Returns current offsets. Okay, write to a file descriptor. I've got the same IO vector tuckable here. Create a directory. All right, create a directory. Return attributes. Pass get. All right, adjust the time stamps. Those sets of times. Yep. This is similar to FD file stats at times. All right. Create a hard link. All right, I'm kind of writing down random things here. I don't expect I'm going to be completely comprehensive with everything, but hopefully I'll get enough information here that it'll help people who are working on this stuff understand what's going on and give them something from which to file a bug report for more specific information when they need it. Kind of what I'm thinking here. Open a file directory. So path open is one of the biggies here. So all right. Going through. Say a few words about what a symbolic link is. Okay, I'm just kind of plowing through, getting closer to the end here, so hopefully we'll be finished up pretty soon. I know it's a long stream, and most people have not stuck with me, and that's totally fine, because it's pretty boring to watch someone else type documentation. But hopefully this effort will help some folks out, or at least give folks like the starting point for which they can ask different questions, which will hopefully help. That's what I'm thinking here. So FD read link, description of symbolic links. Like a file. Okay. This function is pretty subtle. Pull one off. This is one of the biggies here. And we'll come back to it. Do that at the end here. Okay, scheduled. There's nothing. And numbers. This function does not block. This is anticipating some stuff we have in preview 2, where functions, we decided that it's best to have functions that say that it does not block. Okay, there's actually another change, is that random get has changed from being a slow function to being a fairly fast function. So it does not block, and it doesn't see us bring thing, the buffer return. So it never fails. The observation with the failure thing is that it's too error prone for a random number generator to fail, because if you're an application and you need random numbers, there's something you can do in the failure case. And historically, many applications have fallen back to less secure behaviors, which has been a common security hole. So we want to have a random number generator that just doesn't fail. And we can say that the host can deal with whatever situations that arise. The WASI host can deal with whatever situations that arise if random numbers can't be produced for any reason. All right. Slug accepts. I'm going to defer these later, put these in my notes document. Slug functions, and move on to, because preview 2 is doing a more complete socket implementation. There's more that we could say here, and probably should, but I'm low on time here, so I'm going to go to pull one off, which is the really interesting function here that I want to focus on. So it can really pull for set of events. Okay, and that is WASI poll in a nutshell. All right, so I've now done a very, very quick pass over this file. I didn't finish everything I wanted to finish. And one of the things I didn't get to that's actually really important, that's been a common source of questions, is about the ABI, about things like the result types, the out parameters, and those kind of things. And I'd love to do more of that, but I'm going to do that in a different session. So I will then take this offline, and I'll be submitting a PR for this to the WASI repo to submit the documentation that I wrote now. And hopefully this will be a part of a process to continue improving documentation. I think this is just going to be a first step overall. So thanks a lot for people who showed up early. And thanks for people who asked questions. And I will hopefully see everyone around in a future stream.